This presentation is about moment of a force. Lesson objectives. To be able to calculate moments. To be able to use the principle of equilibrium to find unknowns. To understand the impact of tilting. Now, if you've got two particles on a seesaw and one's heavier than the other, then the heavier one will pull the seesaw down. So to balance, we need to move the heavier one nearer to the pivot. So the closer to the pivot, less capable a particle is of turning the body on which it is acting. The moment of a force is a measure of its capability to turn the body on which it is acting. The moment of a force F about a point P is equal to the magnitude of a force F times the perpendicular distance from the point F to the force from the point P to the force F. So, for example, if you know the direct distance and it's x from the perpendicular distance x from the point P to the force F, then the moment is equal to F times x. If you, however, know a distance that is at an angle from the point P to the force F, then we use trigonometry to find the distance. In this case, it would be d sine theta, and the moment would be force times d sine theta. Moments are measured in Newton meters, and in practice it will be the FX version that we'll be using for the M1 exam. Now, a moment can be clockwise or anti-clockwise. So, for example, if we've got the point P, like this, and the force F on the right-hand side pointing upwards, we rotate it round that point P, like so. We find that it moves in an anti-clockwise direction. If we have the force to the left-hand side of the P, but still pointing upwards, we rotate it round. This will have moved in a clockwise direction. Now, equilibrium of a plane lamina under parallel forces, we must have the component of the resultant force in any direction must be zero, i.e. up equals down, left equals right. And the sum of moments about any point must also be zero. If a lamina is not light, then it has a weight, and this weight will act at the centre of mass of the lamina. For a uniform lamina, the centre of mass is at its midpoint. So if we have a uniform rod, AB, of length 6 meters and mass 3 kilograms, pivoted at C where AC equals 2 meters, and we want to calculate the mass of a particle that must be attached to A to maintain equilibrium with the rod horizontal, first of all we should draw a diagram. So we start with the rod AB, pivoted at C, where AC is 2 meters, so 2 meters from the end A. This is definitely not to scale. We have a pivot, which we usually denote by a triangle, and a pivot is keeping that rod from falling down to the ground. So there must be some sort of upward force acting at that pivot, which we're going to denote here by R. We also have a particle that's attached to A, and we're interested in its mass. So we've got the weight is the corresponding force to the mass, which is m times g, and it acts at A. We also need to take into account the centre of mass of the rod. The rod is 6 meters across, so 3 meters across will be the centre of mass, so 1 meter further on from C, or 3 meters from B, we will have a force of 3g, the corresponding weight to a mass of 3 kilograms. So these are all the forces that are acting in this situation, and we're only interested in the unknown m, but we also have an unknown r. Now in these scenarios, where we have two unknowns and we're only interested in one, it's generally best to take moments about the point which has the unknown that we don't care about. So we take our moments about C because we don't care what the force R actually is. Now, when I do this, I tend to draw this as a table. So I list all the forces and their corresponding moments. So starting with the force R, the moment, it's got a 0 perpendicular distance to the point C. So R times 0 is 0 Newton meters, which is the reason why we take our moments about C, is that the R, that unknown, will have a 0 moment and will play any part in any equation that we form. mg is 2 meters away, so perpendicular distance 2 times force mg is 2mg, and if we span it round the pivot C, it would spin in an anti-clockwise direction. Finally, the 3g force, it's 1 meter away from C, so it's 1 times 3g, gives us a moment of 3g. If we span it round the point C, it would spin in a clockwise direction. Now for equilibrium, anti-clockwise moment must equal the clockwise moment. So 2mg must be equal to 3g. We can cancel down the g's to give us 2m is equal to 3. Divide both sides by 2. We get that m is equal to 1.5 kilograms. If we then wanted to find r, the easiest thing would be to stick the 1.5 in for m and do an up equals down on the plane lamina. We'll have an example of that in example 2. So, a uniform beam AB of length 8 meters and mass 20 kilograms rests horizontally on supports at C and D, where AC equals BD equals 1 meter. So 1 meter from the end of each of these, so draw AB like that, and then 1 meter from each side. We draw pivots or supports. So C on the left hand side, 1 meter away from A. I'm going to call the force R C subscript. And 1 meter away from B is my D support, and I'm going to call the force that provides upwards RD. Now a man of 75 kilograms stands on the beam at E, where AE equals 2 meters. So another meter in from C, we have the point E, and the man is 75 kilograms, so a force of 75g downwards. It's a uniform beam, so we'll need a centre of mass again. It's 8 meters, so 2 more meters from the point E to the centre would give us the centre of mass. 3 meters would then take us to D, and we'll have a force of 20g downwards because a mass of 20 kilograms corresponds to a weight of 20g. And we have all our forces then. Now in this case we're being asked to calculate the magnitude of the reactions at each of the supports C and D. So we're interested in RC and RD. Now we'll only be able to get both of these once we've got one of them. Now if we take moments about C, we then make RC a 0 moment and we'll be able to find RD. Similarly, we could have taken moments about D and found RC first. It really doesn't matter as long as you get all the different components correct. Draw my table for the moments diagram, force and moment. So we'll start with the force RC. It's got 0 moment because it goes through the point. Looking at 75g, it's 1 meter away, so 1 times 75g is 75g. We span it round the point C, it would spin in a clockwise direction. We look at force 20g, that's 3 meters away from the point C, 1 plus 2 is 3, so 3 times 20g is 60g, and if we span it round C, it would spin in a clockwise direction. And then the final force is RD. RD is 1 plus 2 plus 3 is 6 meters away, so 6 times RD will be the moment. If we span it round the point C, it would have an anti-clockwise moment. So again, we make anti-clockwise forces equal clockwise forces. Moments, sorry, not forces. Anti-clockwise equals clockwise moments. So 6RD equals 60g plus 75g. 6RD equals 135g. Divide both sides by 6. RD equals 45 over 2g newtons. Now, we could take moments about D to find RC, but at this point, because we only have one unknown, it's best to make up equals down. So up we have RC plus RD, and down we have 75G plus 20G. Sticking in our value of RD and adding the right hand side, we get RC plus 45 over 2G equals 95G. Take the 45 over 2G from both sides, we get that RC equals 145 over 2G newtons. For a non-uniform lambda, the centre of mass is not located at the midpoint. So if it's uniform, centre of mass is in the middle. If it's non-uniform, it's not. And generally the question is to find that centre of mass. So a non-uniform rod AB of length 4 meters and mass 5 kilograms is in equilibrium in a horizontal position resting on two supports C and D, where AC is 1 meter and AD is 2 meters. Magnitude of the reaction at C is half the magnitude of the reaction at D. Find the distance of the centre of mass of the rod from A. So again, as usual, a diagram will help us sort all this information out. So we've got a rod AB, we've got two supports, AC is 1 meter, and AD is 2 meters, so another meter from C is where D is, and we have forces pointing upwards at those two supports, and 2 meters from D to B. So the magnitude of the reaction at C is half the magnitude of the reaction at D. So if we call the magnitude at C R, then D would be twice that, 2D. So that C is half, the one at C is half the one at D. Now we don't know where the centre of mass is from A. The mass is 5 kilograms, so the weight will be 5G, but it's at an unspecified distance. So how we do this is we have X meters coming from A, because we want to actually find a distance from A, and we have a force 5G downwards. It doesn't really matter where you place this, but we will have to make it work in the formula. And in general, if you've got two supports, for it to make sense, the centre of mass will be between the two supports. Now, in this case, we've got two unknowns, R and X, and there's no way we can get a formula that doesn't have Moment's formula doesn't have both in, so it's best to find R first, because an up equals down will quickly allow us to find R. So up we have R plus 2R, and down we have 5G, which gives us 3R equals 5G. Dividing both sides by 3, R equals 5 over 3G newtons. Now in this case, it's best to take moments about A, so that we only have, makes the X simpler to find the moment of the 5G force. We just need to times by the X, and the X doesn't get involved with any of the other points. So that's the easiest way of getting a moment equation from this. So drawing our table, our force moment table, we start with force R. It's 1 meter away from A, so it's 1 times R, 1 times 5 thirds G, so 5 thirds G. We span it around the point A, it would spin in a anti-clockwise direction. The next force is 5G. It's X away from A, so 5GX is the moment. It would spin in a clockwise direction. And then finally, the 2R force, 1 plus 1, 2 meters away from A. So 2 times 2R is 2 times 2 times 5 over 3G, gives us 20 over 3G. If we span it round A, it would spin in an anti-clockwise direction. So again, we make our clockwise equal to our anti-clockwise moments. So our 5GX equals 5 thirds G plus 20 thirds G. We can cancel out the G's, so 5x equals 5 thirds plus 20 thirds. Adding the thirds together, 5x equals 25 over 3. Divide by 5, we get 5 over 3, or 1 2/3 meters. Our final example demonstrates what happens when we have when we are on the point of tilting. So we have a uniform plank AB of mass 10 kilograms and length 2 meters is in equilibrium in a horizontal position resting on two supports at points C and D, where AC equals 0.5 meters and AD is 1.3 meters. A boy of mass 30 kilograms stands on the plank at the point E. The plank is on the point of tilting about D. By modelling the plank as a uniform rod, the boy is a particle, calculate the distance AE. Draw the rod AB, or plank in this case. We've got two supports. AC is 0.5 meters. So 0.5 in from A, we have a support, with C pointing upwards. D, well, the plank is 2 meters across. D is 1.3 from A, so it's 0.7 from B. And again, we have a force coming upwards from there. And we have a boy of mass 30 kilograms stands on the plank at the point E. We don't know where that is at the moment. Let's deal with the centre of mass first. 1 meter in will be the the weight rather, of a mass 10 kilograms is 10 g. 1 meter in, so another 0.5 from C, another 0.3 from D, a 10 g force downwards. We don't know where the point E is, which is where this boy is, but we do know, that the plank is on the point of tilting about D. Now, to deal with the boy, similarly to the centre of mass of a non-uniform lamina, we can make it x meters from the point A, because it's AE is the distance we want to find. Label that point E, and a boy's got mass 30 kilograms, so the weight would be 30 g. Now, when the plank is on the point of tilting about D, basically means that the plank is about to lift off C. It's going to tilt around D. It will no longer be touching C. So at the point it's about to do that, the force at C will be 0, because it's still touching the support, but the support isn't actually contributing any force to keeping it upright. D is taking the full load of that at that point. So we make the force at D R, and the force at C is 0. So that's what tilting means. If it's tilting about D, then the force at the other supports will be 0. So it works out similarly to our last question. We'll start with up equals down to find the R. So 0 plus R equals 30g plus 10g, giving us R equals 40g. We take moments about A, so we can quickly get at the x meters. So force and moment. So a force of 0 newtons will give us 0 newton meters. Force of 30g, which is x away, is 30g times x, so 30gx, and that would spin in a clockwise direction around A. The 10g force is 1 meter away, so 1 times 10g is 10g, and that would also spin in a clockwise direction about A. And finally, the R force, well, R is 40g, it's 1.3 away, so 1.3 times 40g gives us 52g, and if we spun that round A, it would actually spin in an anti-clockwise direction. So again, we make our clockwise equal to our anti-clockwise, so 30gx plus 10g equals 52g. Take 10g from both sides, 30gx equals 42g. Cancel the g's, 30x equals 42. Divide both sides by 30 to get x, so x equals 42 over 30, and 42 over 30 equals 1.4 meters. And this concludes this presentation.